Okay, so I hope you've enjoyed your break. So let's get started. So that was my little introduction to the motivation for from if we want to understand the QCD spectrum, we need to think about resonances because most of them are unstable under the strong interactions. And these decay to multi-particle states, multi-hadron states. And so if we want to understand resonances, we need to understand how multi-particle states interact, which is via the building blocks that describe these interactions, so the scattering amplitudes. And so this forces me to think about scattering theory, and the foundational aspect of scattering theory is the S matrix, which is a unitary matrix, and so this whole section is going to be called unitarity. And so we're going to understand the consequence of unitarity in different ways. Okay. And so just to recap, the S matrix is a matrix that I can write that overlaps states in the far past with states in the far future. We can write this in terms of the time evolution operator and the limit that we take t to infinity. And so if we define some out state as a time evolved initial state, and we force the norm of the states to be unchanged, namely if I require that the out states are normalized the same way that the initial ones are, so we conserve probability throughout our interactions, right? This tells us that if I just rewrite this in terms of the evolution operator acting on the initial state, this I get an S dagger S, and this is this has to be equal to 1 for this equality to hold. So therefore, this matrix has to be unitary. Okay, and this was evident in terms of the context of how we defined it, right? In terms of the time evolution operator, and so this is all that we mean by unitarity. Okay, it's just that the S matrix has to be unitary, and this is, independent of the number of particles that we're thinking about, or the particular matrix elements of the operator that we're considering. Okay, and so here what I want to emphasize, right, is that although the S matrix is beautiful, it's sometimes, some of the contributions to the S matrix is boring, right? It's unitary operator, and so it's gonna encode all possible evolutions of states, including boring ones where you have particles that just don't interact. And really, what we're interested is in teasing out the interactions between particles, and so we define, the more interesting object is not the S matrix itself, but rather the T matrix, where we factor out an identity. Okay, so we pull out an identity. This would tell us that the particles just simply don't interact, and so the T matrix encodes all the beauty, all the dynamics that we're after. And so what is this condition that S dagger S is equal to 1 tell us when we just apply this, we evaluate this while we insert this into S. Okay, and so if I just do I just multiply it out, right, I'll have 1 times 1, which gives me 1. Great. Okay, 1 times minus I T dagger, and I pull out an I, and then 1 plus IT dagger, or IT, right, and I pull out a sign. Okay, and then I'll have I times minus I times T dagger times T, right? This is a mod square of T. And so this is just multiplying out this. And so if this doesn't make sense, stop the video, reproduce it for yourself, right? Okay, so then here I have this identity, right? And then I have 1 on the left, 1 on the right, right? These guys cancel. And so this gives me a constraint on T, okay? And so this is the constraint that T has. So that's a unitarity condition for now rewritten in terms of the T matrix. And so the T matrix has to satisfy this condition. Beautiful. So now we're starting to do something more interesting, okay? And what we're going to do is not evaluate the T matrix in general. That's beyond the scope of what we can do. But what we're going to do is try to focus in the 2-particle sector. Okay, we're going to try to understand how to satisfy this condition, more importantly, how this condition translates into an even simpler object, which is the scattering amplitude. Okay, and so here I'm just going to think about two particles, and in order to define it, and in fact, I'm going to make my life as simple as possible. Okay, so I'm going to assume all particles are identical. They're all scalar mesons. Okay, they could be pseudoscalar, but what I care is that they don't have spin. Okay, that's all I care about. I'm not going to talk about parity, I don't think. And so, whether they're pseudoscalars or scalars doesn't matter. But they're all identical. They don't carry spin, and they have some mass, which I'm going to call m. So m is always going to be the mass of my stable particles. Okay, and so this is like a placeholder for the pion. Okay, so imagine that the whole time I'm just talking about pions, interacting with pions, and the only resonances that we're going to think about are resonances that appear in the pi sector. Okay, and these are all identical. I'm forgetting about electromagnetic charges, anything. Okay, so imagine I'm just thinking about pi plus for simplicity, or pi 0. Okay, so the one particle state, right, I can define in terms of creation operators acting on the vacuum with some normalization of 2 omega, where omega p is the notation that I'm going to be using for the one particle energy, which is just, according to relativity, p squared plus m squared, square rooted. Okay, so omega p is going to be I'm going to use this symbol constantly for describing one particle states, and I'm going to leave the symbol of E, which would naturally describe energy for the total energy of the system, in particular when I'm thinking about two particles. Okay, and so these states, right, are normalized the way that we normally normalize relativistic two particle states with a factor of 2 omega, and then an appropriate three-dimensional delta function. Two particle states, right, I can just define in terms of the momenta of the two particles, right, and two creation operators with appropriate normalization, and then I can define them in terms of direct products if I want. This just have to be symmetrized with a factor of 1/√2. I find this representation much natural and easier. Okay, so then to evaluate the overlap between the two states, just pull out the creation operators for this guy, the annihilation operators for this guy, and then just use the commutation relations between these to then find that you will have a factor of 2 omega for each particle, and then just two sets of delta functions. Okay. All right, so where was I? All right, so if we're thinking about just the scattering amplitude, it's always convenient to think about the center mass frame, well, sometimes more than others, because we're going to be ultimately thinking about lattice calculations where by moving, we're going to be thinking about lattice calculations where the quantities that we're interested in are not Lorentz scalars. If we constrain the spectrum in the center mass frame or a moving frame, we're going to get different spectra. Okay, but these are all going to be related to the infinite volume scattering amplitude, which is itself a Lorentz scalar, which we will always define in the center mass frame. And so we're going to have to get a little comfortable between jumping around moving frames and center mass frames. And the reason why we're going to be using moving frames is because the more frames that we study, the more kinematic constraints that we're going to ultimately be placing in our scattering amplitudes. Okay, and so I'm going to use a notation that is somewhat ubiquitous when thinking about these theories now, these formal aspects, which is when I'm in a moving frame, I will label the total momenta of the system with capital P. I will label the momenta of one of the particles with lowercase k. If these particles are on shell, that tells me that k squared is equal to p minus k squared, which is equal to the mass of the particles. And then the total momenta is a 4 vector, which depends on the energy and the moving momenta. And the The energy, of course, I can write in terms of the center mass energy, which I'm going to be specifically calling E star. Okay, so I'm going to leave the star notation for the center mass frame. And so the moving frame energy is equal to E star squared plus, whoops, typo, let's fix that, P2 squared all square rooted. Okay. So in the center mass frame, where the particles are colliding at each other, okay, center mass, center momentum, I typically call it center mass frame. I'm going to leave everything is going to be labeled with a little star. This is not conjugated. It's supposed to be an actual star. It's kind of hard for me to distinguish between stars and complex conjugation. It's going to be you're going to know the difference between the context, okay? So it's going to be understandable depending on the context. So again, the on-shell condition is that K star squared, right, is equal to this square, which is equal to a mass squared, because each one of these particles are a physical particle. And then the total momentum in the center mass frame, right, is again a 4-vector, where the zero component is equal to the energy in that frame, and then the rest is 0, right? But the 4 momenta of a system, right, is typically, the 4 momentum squared in any frame, right? The 4 momentum squared of a 2-particle system is equal to, it's a Lorentz scalar, right? In any, if I evaluate in any frame, it's going to be the same as in the center mass frame, which is just equal to E star squared, okay? And this, we give the special symbol for S for the Mandelstam variable S, okay? And so sometimes I'll be using E star, sometimes I'll be using S. So just, just keep that in mind, okay? And of course, so the zero, because these are identical particles, we can then, the zero components are of the zero component of this particle and the zero component of this particle are equal to each other because the masses are the same and the magnitudes of the momenta are the same, right? And so this is equal to each other, and so this tells me that that the K0, I can, the zero component of the one of the particles is equal to half of the total energy of the system, right? But that's equal to, by the on-shell condition, equal to m squared plus the spatial part of the momentum squared, all square rooted, right? And so this tells me that from the fact that these are on-shell particles, right, they're identical, I can get the magnitude of their momenta is totally constrained from the energy. Okay, and this is the case irrespectively of whether they're identical particles or not. If they're non-identical particles, this condition gets a little different, but this is just always true. Okay, and so whenever we have quantities that depend only on the relative momenta or the magnitude of the relative momenta of on-shell particles, right, that can translate to total energy of the system or the Mandelstam variable S. Okay, and so studying scattering amplitudes in general is quite taxing, and so we're gonna make our lives easier by just considering a particular kinematic region. And so I'm gonna be showing quite a bit of complex planes for different variables, and so this is the first time I'm showing the complex plane for S, which is E star square, right? And so this is the real axis of S, this is the imaginary axis of S, and we're going to restrict our attention to the kinematic region where only 2 particles can go on shell, so above the 2-particle threshold, but below the 3-particle threshold. Okay, and so we're going to be, in the complex plane, we're going to mostly be restricting ourselves to the real axis. Okay, it's just epsilon above the real axis, above the 2-particle threshold, but below the 3-particle threshold. Okay. And sometimes, and in fact, towards the end of next lecture, we're going to also be analytically continuing this below to think about bound states. And in fact, we're going to consider the complex energy region in general. Okay. So that's my caveat. And so with this, we can then start evaluating matrix elements of the T matrix, okay? And we're going to do this in the center mass frame with a little bit of Buso notation. And so here I'm going to write the two particle states in the center mass frame in terms of, well, the magnitude of them is fixed, right? By the energy, then because the magnitude of the momenta is fixed and the zero components are fixed by the magnitude of the relative momenta, this only leaves a degree of freedom, which is the angular dependence. Okay, and so this finally allows me to then define the T matrix, or the matrix elements of the T matrix, which up to some this is a textbook definition, right? In terms of up to some four momentum conserving delta function, which we can just pull out, that's equal to the scattering amplitude. Okay, and so this T matrix always has this 4 momentum conserving delta function, which we can pull out, and then we have the scattering amplitude, which only depends on S of the system, and then some angles, but in fact it only depends on one of those angles. Okay, so with this, then this allows us to then rewrite this condition, this unitary condition, in terms of the scattering amplitude. And so if we just proceed to evaluate, and I'm just going to write the condition. I have a sketch of the derivation in the back, which I'm not going to bother you with because it starts to get a little too cumbersome, but I left it there for you. So what this gives us is that the imaginary part of M, okay, which is related to matrix elements of the left-hand side, right? The imaginary part of M is equal to the integral, the angular integral, and here I should have said this is this k hat, right? It's just a placeholder for the angle of the vector k, so a solid angle of the vector k in the center mass frame. Okay, so that's what that d little d hat means. So that means d cosine theta k d phi, which is typically denoted as sine theta k d theta k d phi. Okay, so this is a three-dimensional spherical integral. Okay, so this is what I mean by dk hat star. All right, so the imaginary part of M is equal to a two-dimensional integral of 2 dimensions because I have 2 angles, right? Of the complex conjugate of the scattering amplitude multiplying times the scattering amplitude up to some factor of rho, which is the phase space of 2 particles. And so this makes sense, right? This looks like this, right? This looks like a t minus t dagger divided by I, right? This looks like an imaginary part, right? Up to factors of 2, right? T dagger t, that looks like a complex conjugated m times an m, and then there's a phase space factor, which is just some kinematic function, and this kinematic function depends on q star, right, the relative momentum of the system, and then divided by 16 pi over E star, the center mass energy. Okay, so a diagrammatic way to think about this is that if I think about the scattering amplitude of 2 particles, the imaginary part of that is equal to the complex conjugated amplitude times phase space cut, where associated with intermediate particles go on shell, times m. Okay, and so this cut is equal to rho. All right, this is a intuitively way to think about this, and so if this is not quite intuitive yet, don't worry, we're gonna drill this home many times. You're gonna see these kinds of diagrams over and over again. Okay, and so here's my derivation. I'm going to give you my notes. And so I'm not even going to bother walking you through this. It's just basically just kinematics, keeping track of factors of delta functions, evaluating the inserting an identity, evaluating the integrals using those delta functions, and just variable transformation a few times. Okay, so the final thing that we're going to do, close to final thing, is that we're going to diagonalize this identity by this unitarity constraint on the T matrix, which we now have translated into the scattering amplitude. We're going to diagonalize this identity of the scattering amplitude by using angular momentum. Okay, so what we're going to do is just partial wave projector states. This does two things for us, right? It defines states because there's no spin, right? The only angle that, the only source of orbital angular momentum is a spatial orbital angular momentum of the two particles, right? And so this is a good quantum number in our system. And what this will do is that it diagonalizes the unitarity constraint. And so we can define the two particle states in terms of partial wave projected states. Our partial wave projecting wave function is just the spherical harmonics, which are being summed from L equals 0 to infinity, and then the ML is going from negative L to plus L. This is very, very cumbersome, and I'm very, very lazy, and so instead of having two sums with some specific initial and final constraints, I'm just gonna collapse this into a single sum that is with some limits that are undefined, right? And so whoops, I see a typo, so let's fix this. Okay, so my states are defined in terms of L, M, and S, or equivalently E star. Okay, I could have picked one or the other. Okay, I'm gonna try to use S as much as possible, but sometimes I use E star. All right, so the spherical harmonic, what it does, right, is that it just takes into account the angular dependence that is unconstrained from the on-shell condition. Okay, and so this spherical harmonics is just keeping track of that. And so then with this, and remembering that the scattering amplitude is defined in terms of matrix elements of the T matrix, using these states, right, and we just pull out the partial wave projected states and the spherical harmonics. What you can show easily is that the scattering amplitude is just defined in terms of, well, easily if you don't make typos, right? It's much easier if you don't make typos, right? I forgot about this factors of square root 4 pi. So you have a spherical harmonic associated with there's like typos galore. Look at that. So you have partial wave spherical harmonic associated with the final states, a spherical harmonic associated with the initial state. These are one of them is conjugated because it's associated with the initial state, and the other one's not conjugated because it's coming in with the final state. Okay. And if you want to remember, understand why this is star versus unstar, I mean it's a convention, but you can imagine that here we're creating a state, so we're diagramming our states, including our operators, including the spherical harmonic wave function. Okay, if you want. And so the scattering amplitude in the infinite volume world, well, angular momentum is a good quantum number, and so it should be diagonal in L, right? So this is a matrix that is diagonal in L, okay? But azimuthal symmetry is also a good quantum number. So unless we introduce some external magnetic field, let's say, that then makes introduces some hyperfine splitting or something associated with M, the scattering amplitude itself is diagonal it's independent of M. Okay, so it's the same for all the M's for a given L. So it only depends on L. Okay, and so then I can write M, L prime, M prime, L, M in terms of single scattering amplitude, which depends on L, and then a bunch of Kronecker deltas, okay? And so if I then insert this condition, I put it back into my previous condition, my previous equation, namely this one, boop, right? Well, what is the spherical harmonics? The spherical harmonics, what are they going to do? They're just going to collapse this integral. You can just evaluate the integrals explicitly. And so you're just going to get, after a little bit of work, what you will have is this identity for the so after a little bit of work, what you're going to have is just for each component of the scattering amplitude, you're going to have this condition that the imaginary part of the partial wave projected scattering amplitude of the Lth component is equal to the mod square of the Lth component of that same scattering amplitude times rho. Very, very simple. So by partial wave projecting, we grab this matrix relation, which then got translated into an integral equation down to an algebraic equation. Beautiful. So simple. All right. So partial wave projecting does a whole lot of work for us, and it allowed us to write this unitary condition quite simply. Sometimes we'll want to think about the S matrix in terms of, or rewrite the unitarity condition of the S matrix in terms of introducing a scattering phase shift, right? And so the partial wave projected S matrix we can write as a single phase in terms of a single phase, which is the scattering phase shift, right? So if the particles don't interact, the phase shift would be exactly 0, and this would just be 1, consistent with our definition of, or our intuition for the S matrix, right? And so we can rewrite this in terms of the scattering amplitude. So we could follow all the steps, right, and take care of the normalization. So I'm just skipping some steps here. So the S matrix, the partial wave projected S matrix, we can write as 1 plus 2I rho ML, right? And so then this allows me to then rewrite the scattering amplitude in terms of the scattering phase shift. All right. And so just algebra at this point, right? I subtract from both sides 1, right? I divide by 2I rho over here, right? I can rewrite this. I can pull out, typo. I can pull out a phase, right? So I can rewrite this as e to the I delta times something that looks like a difference of e to the I delta and e to the minus I delta, right? Divided by 2I, that's equal to sine delta. Stop the video if that doesn't make sense, right? And then the next step, I just rewrite this as, I can pull this out and bring it to the denominator and rewrite it as e to the minus I delta in the denominator, right? That I can write as cosine minus I sine theta, or sine delta, sorry. And then I have sine, that becomes 1, sine, cosine, that becomes cotangent in the denominator. And so I can rewrite it as this. Okay. And so this is another way, this is a way for us to write explicitly the scattering amplitude in terms of the scattering phase shift. And what you can check, right, is that the imaginary part of M here has to be, right, equal to the scattering amplitude mod squared times rho, right? That's exactly what we just said was a grand unitarity condition for the scattering amplitude. Okay, so here we haven't said anything about the scattering amplitude. Now here we're rewriting the scattering amplitude in terms of scattering phase shift. So why don't you go ahead and check that. All right. That seems like a great point to stop. So this is my mini review on unitarity. Next, we're going to think about how to derive these conditions, but now using a diagrammatic representation of scattering amplitude. Okay, so I'll see you in the next video. Bye.